Well, hello Year 11, and I hope that you're all safe and well wherever you are during the current crisis, and that you are continuing to keep up with those subjects that you intend to take further. This video is aimed at those who want to go on to do chemistry at AS level and A level, so the rest of you are welcome to tune out now. What I thought I'd do is give you an indication of the sorts of skills that you really should have mastered at GCSE that we will take almost for granted at A level. Because lots of students come into Year 12 without knowing or remembering the basics. And one of the things I always do at the start of the year is I ask my students, what is a mole? And it is amazing how many of them cannot answer that question. Even the students who got 9s at GCSE are unable to answer that question. So have a think and then see if you've got the right answer. Well, let's start with what it is not. A mole is not 6.02 times 10 to the 23. If you gave that number, what you've actually given is Avogadro's number. And that is important and it is related to a mole, but that's not what a mole is. The definition on Wikipedia is that it's the unit of measurement for the amount of substance in the International System of Units. It's an SI unit for the amount of substance. Just like mass is measured in kilograms and time is measured in seconds, chemicals are measured in moles. And the reason for that is, let's say we were describing how many people went to a football match, and I said, 10,000 people went to that match. That makes sense. What doesn't make sense is to talk about 500 tons of people and give them mass. What we want to know is the number of individuals, not the combined amount of flesh that was in that stadium. And in some ways it makes just as little sense to talk about 1 kilogram of copper sulfate, because as chemists what we're interested in is the actual number of copper sulfate particles that are there. So we want to work in moles, so we actually have an idea of how many particles there are, not in terms of a mass, which obviously doesn't give us anywhere near as much information. To me, this is a mole. It doesn't weigh anything, but what it does have is it has a certain number of slots into which you can put something, and the number of gaps is always the same. It weighs nothing, but it holds a fixed number of items. So this would be a mole of hydrogen atoms, each one of these slots holding a hydrogen atom, and when it's full, that is a mole of hydrogen. Note, it doesn't make sense to talk about a mole of anything really but a pure substance, so each one of these slots must hold the same thing. So pause the video and have a think about what these might represent. Well, hopefully you recognise on the top left that the black balls here, that's carbon, so that would be 1 mole of carbon. On the right hand side, well, half the slots are filled, so that would be 0.5 moles of carbon. Down here, if each one of these is a mole, we've got 2.5 of them, so that's 2.5 moles of carbon. And here, for those of you that are really on the ball, you might recognise that as oxygen. So that's 1 mole of oxygen. What would this be then? Pause the video, have a think. Well, you may know that actually a mole doesn't just have to apply to atoms, it can apply to many other things here. And if we look on this particular well here, we can see that this well, and indeed every other well, is holding an oxygen molecule. And here we can see actually that we are 2/3 full. We've got 2/3 of a mole of oxygen molecules. This, have a think. Well, hopefully you recognise that this is the classic Mickey Mouse shape of water, and what we've got here is we've got 2/5 of a mole of water, 0.4 moles of water molecules. the mole is actually just a very simple idea. It is just a specific number of particles. So which of these boxes would be heavier and why? 1 mole of helium or 1 mole of sulfur? Well, I hope that you've realised that each of them contains the same number of atoms. Each of them is just a full tray of the atoms. But this atom weighs 4 atomic mass units, whereas the sulfur atom weighs 32 atomic mass units, and that's because of the number of protons and neutrons in the atom. Because it's the same number of particles, if this particle is 8 times heavier, then it means that this tray, this mole, is 8 times heavier. So the boxes contain the same number of particles, but because sulfur particles are 8 times heavier, the box on the right would be 8 times as heavy. Moles are very closely related to relative formula mass, and 1 mole of hydrogen, if I put a hydrogen atom in every single one of these slots and fill up a mole, that weighs exactly 1 gram. And that's not a coincidence. In fact, the number of particles, the size of the tray, the number of gaps has been chosen to make that true. So how heavy are these? Pause the video, have a think. Well, hopefully you realise that that particular atom is 12 times as heavy as hydrogen, and therefore the whole tray is 12 times as heavy as a hydrogen, so it weighs 12 grams. Similarly, this oxygen atom is 16 times as heavy as a hydrogen atom, so the whole tray is 16 times as heavy as a tray of hydrogen, a mole of hydrogen, so it would weigh 16 grams. In fact, a mole is defined, and you do need to know this at A level, defined as the number of particles in exactly 12 grams of the isotope carbon-12, which means 1 mole of hydrogen is 1 gram, 1 mole of helium atoms is 4 grams, 1 mole of potassium atoms is 39 grams, 1 mole of lead atoms is 207 grams, because 1 atom is 207 times, so any particular number of atoms, 1 mole of atoms, is also going to be 207 times. In other words, 1 mole of an element weighs the relative atomic mass expressed in grams. 5 moles of hydrogen, well, if each mole weighs 1 gram, the whole lot weighs 5 grams. Pause the video, have a think about how much these would weigh. Well, this is half a mole of carbon, and we know that the whole thing, the whole tray, would weigh 12 grams, so half a mole of carbon would weigh 6 grams. And if 1 mole weighs 12 grams, 2.5 trays would weigh 30 grams. And we get our familiar equation: mass is the relative atomic mass times by the number of moles. By A level, you really shouldn't be relying on your triangles. You may have used mass, moles, MR to help you get by. At GCSE, that needs to stop. You need to understand these equations. You need to be able to work them out without learning them, because when you are combining equations, you haven't got time to try and draw out triangles and work it out. Have a think, which of these boxes would be heavier? 0.8 moles of silicon, 2 moles of carbon. Well, hopefully you've realised that silicon has a formula mass of 28, so the whole tray would weigh 28 grams, and if we've got 4/5 of a tray, 4/5 times 28 is about 22.4 grams from memory. Over here we've got 2 moles, each of those moles of carbon weighing 12 grams, so that is 24 grams. Let's see if I've got my maths right. There you go, 22.4 grams and 24 grams. What about this one? Be careful here, there is a sting in the tail. Okay, so 4 moles of carbon, each one of those weighing 12 grams, so the total mass there would be 48 grams. Over here on the right hand side though, chlorine is diatomic. So actually we're talking about Cl2 molecules. And if we're just talking about a mole of chlorine or 0.4 moles of chlorine, we mean Cl2. Again, we would just expect you to know that at A level. This is clearly 2/5 full. So 0.4 moles of chlorine, 28.4 grams. The chlorine would be slightly heavier. A mole is a specific number of particles. As long as it's the same, you can put anything you like in those slots. It doesn't just have to be atoms, it can be molecules, it can be ionic compounds. Have a think about how heavy these would be. So on the left, we've got 2/3 of a mole. The tray is 2/3 full. And if it were full, it would weigh 32 grams. So 2/3 times 32 is about 22 grams. Here we've got 1/5 of a mole. We've got one row out of 5 full. If it was full, it would weigh 16 grams. So 1/5 of 16 grams is going to be around 3 grams. And notice that we did all of those calculations, every calculation about moles and mass, without ever knowing how many particles were in a mole. In my fake mole, there were 30 particles, but in reality, there are quite a few more than 30 holes in a mole. If you know your Only Fools and Horses, stick a pony in my pocket. Well, a pony is £25. A monkey is £500, a grand is £1,000, and that's because when working with large numbers, it might be easier to talk about 2 monkeys or 3 ponies. Slightly easier. A mole, though, is a huge number of particles. In fact, it's such a large number that we almost always write it in standard form, 6.02 times 10 to the 23. You will use this number so much at A level that actually you will just get to know this. It is provided for you on a data sheet, but actually knowing that number is very helpful. You can begin to see why we use moles now, of course, because if we were describing the number of particles in every chemical, the numbers would be huge and unmanageable. This number that some of you may have quoted right at the start is known as Avogadro's constant, but it's worth pointing out that Amedeo Avogadro never knew this number. It was only determined 54 years after his death. People have been using moles for half a century without ever actually knowing how many particles were in a mole, and it just goes to show you don't need to know the number of particles in a mole to be able to use it, and most students at GCSE will not know that number and won't ever need to use it. Unfortunately, at A level, you do need to. So let's have a look at an A-level question. An A-level question might look like this. How many hydrogen atoms are there in 90 grams of water? Well, the first thing we can do is we can work out the number of moles. We know that 1 mole of water, 1 tray of water, weighs 18 grams. And therefore, there are 90 divided by 18, which is 5 moles, 5 trays of water. Each of those moles has 6.02 times 10 to the 23 slots. So the total number of molecules we have is 5 times 6.02 times 10 to the 23, which is 3.01 times 10 to the 24 water molecules in total. So we've got that number of these in that 90 grams of water. But the question asks us how many hydrogen atoms are there? And so we need to look here and see that in every water molecule there are 1, 2 hydrogen atoms. So if we know that there are this number of water molecules, there must be twice that number of hydrogen atoms. Each molecule has 2 hydrogen atoms, so there are 6.02 times 10 to the 24 hydrogen atoms in 90 grams of water. Here's a very similar question. Have a think. How many hydrogen atoms in 100 grams of methane? Pause the video, see if you can work it out. Well, the first thing we would do is we'd work out the number of moles. 1 mole, one tray of methane weighs 16 grams. And so we know that we've got 6 1/4 moles, 6 1/4 of these trays of methane. We know how many methane molecules there are in a tray. Each box has got this number of slots. And therefore, the total number of methane molecules, the total number of these is 3.76 times 10 to the 24. If we look at one methane molecule down here, we can see that there are 1, 2, 3, 4 hydrogen atoms. So if there's that number, 3.76 times 10 to the 24 molecules, times that by 4, and we get the number of hydrogen atoms in 100 grams of methane. These are the sorts of questions that you will get at A-level. Each one of these is multiple choice, which you might think is great, until you realise you've only got 1 minute to answer each of these questions. So you do need to be very familiar with every single formula you're going to use and exactly how you're going to use it. So let's have a look at some of these. The Avogadro constant is equal to the number of. Okay, so let's think about 1 mole of sodium chloride. That means we've got 6 times 10 to the 23 NaCl particles. That's 1 mole of NaCl. But each one of those has got an Na plus ion and a Cl minus ion. So that actually has 2 moles of ions. So that's no good. Atoms in 1 mole of hydrogen gas. Okay, so we've got 6 times 10 to the 23 of these. But again, each one of these has got 2 hydrogen atoms. So again, we've got 2 moles of hydrogen in that. Electrons in 1 mole of helium. Well, again, we've got 6 times 10 to the 23 of these. But helium's got 2 electrons. So again, we've got 2 moles of electrons. But the number of molecules in 1 mole of oxygen gas, that means we've got 6 times 10 to the 23 of these, which is 1 mole. So the answer is D. A question that my A-level students get wrong again and again, despite the fact they've seen it 3 times, is what is the Avogadro constant equal to? Well, it's not the number of grams of an element which contains 6.02 times 10 to the 23 atoms of that element. So 6.02 times 10 to the 23 atoms of helium, for example, weighs 4 grams. And 4 is certainly not the Avogadro number. Particles required to make 1 gram of substance. Well, it takes the Avogadro's number of hydrogen to make 1 gram of substance, but if we're talking about helium again, to make 1 gram of substance, we only need 1/4 of a mole. So it's certainly not that. B and C look the most promising. But as we've seen above, 1 mole of oxygen actually, and 1 mole of hydrogen actually contain 2 moles of atoms. So it's not that, so it must be the number of atoms contained in 1 mole of any monoatomic element. So if we've got 1 mole of neon, 1 mole of argon, 1 mole of krypton, that is a mole of atoms. But this is the first one that I think will really bring home to you what you need to do. You've got 1 minute to answer this question. Calculate the total number of atoms in 8.5 grams of CH2Cl2. Right, first thing, moles is mass over MR, no time to write a triangle. So the mass we're given, 8.5 grams divided by 85. You've got to be comfortable enough with just mental arithmetic. You're not resorting to a calculator. At this point, that's the number of moles of CH2Cl2. So let's work out the number of molecules. So times that by 6 times 10 to the 23, and we get 6 times 10 to the 22. Again, no time to put that in a calculator. That's the number of molecules of CH2Cl2. But CH2Cl2 has 5 atoms. So we need to times that by 5, 30 times 10 to the 22, or 3 times 10 to the 23 atoms. Haven't got time to use a calculator here, need to be good with mental maths. Moving on to the final two, what is the number of atoms present in 3.06 grams of carbon dioxide at 373 K, where the molar volume is 30.6. So that is the volume of 1 mole. So again, number of moles is the volume we have over 30.6. Again, it's not an equation you're going to know, but you've just got to be familiar enough with these numbers to know that whereas you would have used 24 at GCSE because you're always talking about 298 Kelvin, here you need to know that moles is the volume of gas over the molar volume. So that's 0.1. So 0.1 moles of carbon dioxide. Let's talk about the number of molecules. Times that by 6 times 10 to the 23, and that gives us 6 times 10 to the 22 CO2 molecules. But CO2 has got 3 atoms, so times that by 3 is 18 times 10 to the 22, or 1.8 times 10 to the 23 atoms in CO2. There we go, C. Now question 17, you might be thinking, how on earth am I going to do all of this in 1 minute? So let's have a look at it. Right, number of moles for A is 500 divided by 1,000, that's the volume in decimeters cubed, times by the concentration, and that gives 0.5 times 0.1, 0.05. We've then got to times that by 6 times 10 to the 23, which will give us the number of particles. And then we realise sodium sulfate. Sulfate is a single negative ion, SO4 2-, so we times that by 1. If you wanted to work all that through, you can do, but we'll see why that's not necessary. For B, 250 centimetres cubed, again, we're going to divide by 1,000. And we're going to times that by 0.12. So that is a quarter of 0.12, which is 0.03, times by 6 times 10 to the 23 to get the number of particles. And then there's 2 negative ions. We'll look in a later video about this. Many students can't split this up, but barium chloride, there's 2 negative ions there. Part C, we've got 250 centimetres cubed. We would have to divide that by 1,000 to get the number of decimeters, times by 0.15, which is a quarter of 0.15, or 0.0375 off the top of my head, times by 6 times 10 to the 23. There's 1 negative ion, times 1. And finally for D, we would do 500 divided by 1,000 to get the total number of decimeters cubed, times by 0.1, which is 0.05, times by 6 times 10 to the 23. And then again, look here, zinc nitrate, zinc 2+, NO3-, NO3-. So there's 2 ions. Now the key thing here, and the reason you can do it in a minute, is by realising that in every case you are dividing by 1,000. So let's not do that. In every case you would be multiplying by Avogadro's number. We're just asked for the greatest number of negative ions, so let's not do that. Okay, so here we can begin to see a way through, especially if we simplify this to a relative factor of 2, 1, 1 and 2, which is the relative amounts. So now we've got 2 times 0.1, which is 0.2 times 1, gives us a relative factor of 0.2. 1 times 0.12 times 2, 0.24. 1 times 0.15 times 1, 0.15. 2 times 0.1, 0.2 times 2, 0.4. So we can simplify the maths by realizing what we're going to do the same every time. And in every case we were going to divide by 1,000 to put it in decimeters cubed. In every case we were going to multiply by Avogadro's number. The crucial thing is the relative volume, the relative concentration, and the number of negative ions. And put like that, we can begin to see how we can do that sort of mental maths in a minute. I hope this was useful, and I hope that actually if you do have any questions you will email me. My email address, don't use show my homework, a.nixon@ulstergs.com. And I hope that you're well. Continue to enjoy the good weather.